Last time we derived the solution to the least squares problem in some special cases. Today we're going to look at the singular value decomposition, which is a useful way to understand the least squares problem at a deeper level. The singular value decomposition, or SVD for short, just takes a matrix A that's an m by n matrix and decomposes it into the product of three matrices, U times sigma times V transpose. And these matrices U, sigma, and V have certain special properties. So first, U is an M by R matrix. So it has R columns, and these columns are orthonormal. So this means any pair of columns, if we take the inner product between them, we get 0, unless we're looking at the same column. So the inner product between U1 and itself is 1. And if we write this out in matrix form, that gives us an identity like U transpose U equals the identity. Note that in general, U transpose will not be equal to the identity. Just because we have orthonormal columns does not mean we will have orthonormal rows. There are some special cases where this holds. We'll talk about this in a little bit. Second, V is an N by R matrix, and it's very similar to U. So V has R columns. These columns are orthonormal. Again, we can't expect that VV transpose is equal to the identity in general. And then finally, we have sigma, which is an R by R diagonal matrix with entries along the diagonal denoted by sigma 1 up to sigma R. All the other entries are 0. And by convention, we always assume that the entries in the diagonal have been sorted so that sigma 1 is the largest and sigma R is the smallest. So they're sorted in decreasing order. And we call these sigma the singular values of the matrix A. Now there's a little bit more that we can say about the structure of U and V, but to do that we're going to have to recall the notion of an eigenvector and an eigenvalue. So recall that we say that V is an eigenvector of a matrix B if we can write B times X equals lambda times X, so that B times X is just a scaled version of X, where that scaling factor, lambda, is what we call the eigenvalue. And recall that this is in general, a complex number. Note that even if B contains only real entries, lambda may still be a complex number. But it's a useful and handy fact that often will simplify things, especially in this class, that anytime we have a symmetric matrix, the eigenvalues of a symmetric matrix are always all real. A particularly important subset of symmetric matrices are what are called positive semi-definite matrices. And a positive semi-definite matrix is a symmetric matrix with, of course, real eigenvalues. But those eigenvalues are all non-negative, so they're greater than or equal to 0. We will encounter positive semi-definite matrices throughout this class, so this is an important definition to keep in mind. Okay, so let's get back to the SVD. So what else can we say about the SVD? Well, one thing is that U1 up to UR, the columns of the matrix U, are actually the eigenvectors of the matrix A transpose. So A itself doesn't have any eigenvectors because A isn't a square matrix, but A transpose does, and U gives us the eigenvectors of that matrix. To see this, first note that A transpose, if we just express A in terms of the SVD, we can write it as U sigma V transpose times U sigma V transpose. Now if we distribute the transpose on the second version of this matrix, we have to swap the order and we get V times sigma, which is a diagonal matrix, so it doesn't change when we apply the transpose, times U transpose. And now in the middle we have V transpose V, which is just the identity, and then we get U times sigma sigma U transpose. And remember, sigma is a diagonal matrix, so sigma times sigma is just sigma squared, where sigma squared denotes the same matrix as before, but with sigma squared along the diagonals. So now we can use this fact and observe that A times A transpose times UM is just U times sigma squared times U transpose, that's what A transpose is, times UM. And now let's look at U transpose times UM. U transpose is just the matrix with rows given by U1 transpose up to UR transpose. So when we compute this matrix vector product, we're computing the inner product between each of the UIs and this vector UM. And when we do that, we're going to get all zeros except for a single 1 in the mth element, because the columns of U form an orthonormal set. And we can denote this vector by E sub m, so this is common notation for the vector that has all zeros except for a single 1 in the mth element. So if we go back over here, we plug in U transpose UM with EM, and then we say, well, what is sigma squared times EM? Well, that's just going to give us EM back, but with the 1 replaced by sigma m squared. So we can pull that sigma m squared out front, and then we're left with U times EM, which is just the mth column of U, or UM. And so we've shown that UM is indeed an eigenvector of AA transpose, and we've also shown that sigma m squared is actually the corresponding eigenvalue. By essentially the exact same argument, you can show that V1 up to VR are the eigenvectors of A transpose A. And just as before, sigma 1 squared up to sigma r squared are the eigenvalues of A transpose A. So in fact, sigma 1 squared up to sigma r squared are the eigenvalues of both AA transpose and A transpose A. When I think about the SVD, I always have a certain picture in my mind. To make this picture precise, let me just first point out that one of the key parameters here in the SVD is R, which is the rank of A. Formally, the rank of A is the maximum number of linearly independent columns or rows. That tells you immediately that the rank is always less than or equal to M. It's less than or equal to N. Together, these two imply that the rank R is always less than or equal to the minimum of M and N. Now, if R is equal to the minimum of M or N, then that means that A is what's called full rank. So I said that that was the traditional notion of how you define the rank. For myself, I really just think of the rank of a matrix as being the number of columns in U and V when you compute the SVD, or the number of non-zero singular values. Now let's assume for the moment that A is full rank. We can really divide the problem into 3 different cases. So sometimes M is greater than N. This is what's called the overdetermined case. So we have more rows than columns. In this case, we can draw a picture where A is a tall, skinny matrix. And in this case, M is going to be much bigger than R. So U is a tall, skinny matrix. But sigma and V transpose will be square matrices. In contrast, if M is less than N, this is the underdetermined case, A is kind of a short, fat matrix. And in this case, we have the opposite setting where N is much bigger than R. And so this gives us a square matrix U and sigma, and then a fat matrix V transpose. Remember, V is an N by R matrix, so V transpose is going to be R by N. Finally, we have the case where M is equal to N, and in this case, if we have a full rank matrix, A is just equal to U sigma V transpose, where all of these are square matrices. So one particular note of caution. In most popular software packages, such as MATLAB or Python, if you ask to compute the SVD of a matrix A, it will return matrices U, sigma, and V, but they are different than what I have just described. In particular, the dimensions will be different. So it will return matrices that I will call U tilde, sigma tilde, and V tilde, where U tilde is M by M, sigma tilde is M by N, and V tilde is N by N. So how do these relate to the matrices I just described? Well, U tilde is simply the concatenation of U with some additional columns, denoted U naught. So we have the R columns from U and the M minus R columns from U naught to form an M by M matrix. V tilde is the concatenation of the original V, which had R columns, with an additional V naught, which has N minus R columns to make an N by N matrix. And sigma tilde is just the M by N matrix you get by taking a matrix of all zeros and putting sigma in the first R rows and columns. Now, because of all the zeros in sigma tilde, if you actually compute the product of U tilde, sigma tilde, and V tilde transpose, basically sigma tilde cancels out the influence from U naught and V naught in U tilde and V tilde. And so this is exactly the same product as U times sigma times V transpose. So we're just as entitled to consider U tilde, sigma tilde, and V tilde transpose as the SVD. They satisfy the same properties as before. They are orthonormal, meaning they have orthonormal columns. But now, because they're square matrices, and because of a fact that you'll prove on the homework, we also have the fact that U tilde transpose is equal to the identity, as well as V tilde transpose. And sometimes this is useful to have, So by default, this is often what software packages produce. So what does the SVD have to do with least squares? Well, recall that previously when we looked at the least squares problem, which I'm going to rewrite here, we had argued that the solution would be given by x hat equal to A transpose A inverse times A transpose Y in the case where A transpose A is invertible. Now what happens if we just replace A with our expression from the SVD everywhere? So first of all, note that A transpose A is going to be given by V times sigma times U transpose times U times sigma times V transpose. And U transpose U is just simply the identity. So we're left with V times sigma times V transpose, which is just V sigma squared V transpose. This also means that A transpose A inverse is going to be given by V times sigma to the minus 2 V transpose. So sigma to the minus 2 here simply means the matrix with 1 over sigma squareds along the diagonal. So there are many different ways to prove that this is the inverse. It's actually a consequence of something called Sylvester's matrix theorem. But once I write it down, it's also very easy simply to check. So if we just simply consider V times sigma squared times V transpose and apply what I'm calling the inverse here, V times sigma to the minus 2 V transpose, by multiplying these together, we get V transpose V equal to the identity. And then we have sigma squared times sigma to the minus 2, which will again be the identity. And we're left with VV transpose. Now, in general, V transpose is not equal to the identity. But here, we're assuming that A transpose A is invertible. This actually means that A is full rank. So V is actually a square matrix here. And so in this special case, VV transpose is equal to the identity. So if we use this fact, we can re-express our previous least squares solution as V times sigma to the minus 2 times V transpose times V times sigma times U transpose times Y. So again, V transpose V is the identity, and we're left with a sigma to the minus 2 times sigma, which is just sigma to the minus 1. And this gives us this simple form of V sigma inverse U transpose Y. So an equivalent way to write the solution to the least squares problem is just that x hat is V times sigma inverse times U transpose Y. But this way of thinking about the least squares solution has a number of advantages. So for one, this formula actually works even if A transpose A isn't invertible. And you can show that this does actually give the least squares solution regardless of the rank of the matrix A. Moreover, it also gives us a solution to a related least squares problem. So specifically, let's return to the underdetermined case when m is less than n. So if we think about this for a little bit, we realize this is kind of a different problem than what we've been considering so far. So in this case, there are actually many possible x such that y is equal to ax. And the problem here is how do we actually choose one of the possible x's that agree with our measurements? And here, an approach that might make sense is to say, well, let's pick the smallest x that agrees with our measurements. And we can write this as an optimization problem. So we'd like to minimize overall x in Rn, the L2 norm squared of x subject to y equals ax. So it turns out that you can show that the solution to this optimization problem is also given by V times sigma inverse U transpose Y. Finally, we can also consider the square invertible case where m is equal to n. And in this case, it's not too hard to show that V times sigma inverse times U transpose, well, it's just going to be the inverse of A. So this formula has quite a lot of flexibility. But it also helps provide some insight into how least squares is going to perform in noise. So suppose that rather than observing y equals ax, we observe y equals ax plus e, where e represents some kind of noise or perturbation. So if we then form the least squares estimate, which I'll denote x hat ls for least squares, we get simply the pseudo-inverse times y, which is just the pseudo-inverse of a times ax, plus the pseudo-inverse of a times e. To understand how much error has been incurred by the addition of this perturbation e, we might want to compare x hat ls to the clean estimate we would get if e had not been there. So we'll denote this x hat clean, and this would simply be the pseudo-inverse of a times ax without an e. So this means that the size of the error that we're incurring can just be represented as the L2 norm of the pseudo-inverse of a times e, which if we use our SVD-based formula is just the L2 norm of v sigma inverse U transpose e. So now we can ask the question, well, just how bad can the error be? So to think about this, we might actually think about a maximization problem where we say, let's maximize the amount of error that we can get over all possible choices of E in Rm. Now, if we don't add any constraints, E could just go to infinity and we'll get as much error as we want. So we'll add the constraint that the norm of E should actually be equal to 1 and say, among unit norm perturbations, how much error can we possibly incur? Now this is a little ugly, but we can simplify it a little bit. So first, note that we're working with the norm squared of v times some vector. Well, the norm squared of v times any vector, call it z, can just be expressed as z transpose v times z, but v transpose v is just the identity, so this is just equal to z transpose z, or the norm squared of z. So the presence of v here doesn't actually have any impact on the norm, so we can equivalently write this as the problem of maximizing the norm squared of just sigma inverse u transpose e. Again, subject to the constraint that the norm of e is equal to 1. Now this is still just a little bit ugly, but what we can do is kind of relax this optimization problem with something that looks a little bit simpler. So instead of dealing with u transpose times e, let's just replace u transpose e with an arbitrary vector beta in r-dimensional space, and we'll have the constraint that the L2 norm of beta is less than or equal to 1. So why can we actually do this? Well, there are two issues here. So first of all, now we're optimizing over all possible beta, whereas in the previous problem, we were only looking at vectors that lived in the span of the columns of u transpose. So here we're actually considering more possible vectors, so you might worry that we're actually going to come up with something that makes the error even worse. We'll deal with that in a minute. But the other issue is the constraint. So before we said that E had norm 1, and now we're replacing U transpose E with some vector beta and saying that beta should have norm less than or equal to 1. But this is okay because it's actually not that hard to show that if the L2 norm of E is equal to 1, then the L2 norm of U transpose E has to be less than or equal to 1. To see this, recall when we were talking about the sort of extended version of the SVD where we had U tilde, which consisted of U and U naught. And U naught was sort of the orthonormal columns that turned U into a square matrix. Well, if we use U tilde here, the norm squared of U tilde transpose times E is just going to be E transpose times U tilde times U tilde transpose times E. And since U tilde is a square orthonormal matrix, U tilde transpose is the identity. And so we just have E transpose E, which is the L2 norm of E. So if we use U tilde, the norm of U tilde transpose E is just the same as the norm of E. Now, let's look at U tilde transpose E. Well, what is U tilde transpose E? It's just the inner product between U1 and E, U2 and E, all the way up to UR and E, all the way up to UM and E. Now, U transpose E is just the first R elements in this vector. And so when we take the norm of this, we're just adding up the squares of all of these entries. The norm of U transpose E has to be less than the norm of U tilde transpose E, which is just the norm of E, or 1. So we can show that the norm of U transpose E is less than or equal to 1 here. And so the bottom line here is just that this relaxation makes sense. The only thing we have to worry about is whether or not the beta that achieves this maximum actually can be expressed as U transpose E for some vector E. And we'll return to that in a minute. And just note that this optimization problem is relatively straightforward. It turns out, this is something you will argue in the homework, that the solution is given by a beta that has a single 1 in one entry, the entry corresponding to the largest element of sigma inverse, and it will be 0 everywhere else. And so what that means in this case is that this maximization problem just boils down to which one of these entries are we going to pick. We're going to pick the element where 1 over sigma r is the maximum. And then we're looking at the square of this. So we're going to have 1 over sigma r squared, and we're going to take the maximum. And remember that these sigma r's are ordered in decreasing order. So when we're taking 1 over sigma r, the largest value is going to be attained for the smallest singular value, or sigma capital R. So finally we have the solution here as 1 over sigma capital R squared. And now let's return to this concern I mentioned before. Does the beta that has a single 1 in the entry that selects sigma capital R, does that actually correspond to U transpose E? Well, yes, actually. It just corresponds to setting E to be equal to U sub capital R, or the singular vector in U corresponding to the rth singular value. So finally, returning to the reconstruction error, we now show that the penalty that we incur by the inclusion of E, which you'll recall was the norm of V times sigma inverse times U transpose E, can potentially be up to 1 over sigma capital R squared times the norm of E squared. So this is a worst case bound. So there are many perturbations that won't give you error quite this large, but the main thing to notice here is that if sigma r, so if the smallest singular value is too small, then this error can be potentially very bad, and this is something we do have to worry about. In the homework, you'll see some ideas about how you might be able to mitigate this effect.